So first, I would like to give you a brief introduction about what situation about the 3D print medical device in Taiwan. So first, we have to know about the first all this kind of regulation is covered by our Ministry of Health and Welfare, and we have this administration, which is TFDA. They manage the regulatory, and so currently medical device is included in these food, drug, and cosmetics. But however, they have a very specific the class for the medical device. So which means that it's not necessary to wait for that long, like drugs. If we create a new drug, medical device, once we pass this regulatory, we can start it to go to market further. So regulation is top number one concern in medical application. The reason we say that is because we have to consider the risk and what happened, the consequences afterwards. So that's the reason we start to talk about regulation in the beginning is because 3D print in the beginning is some of the challenges, but because the regulation is not very clear. So, but right now we have this guideline already. So let me. Okay, good. Thank you. So the regulations for medical device in Taiwan, basically we developed into three classes like FDA. So we have a class 1, class 2, and a class 3. So if we consider in the class 1, which is low risk, would be very quickly. But however, we have to get this first. We have to get this good manufacturing practice for your medical device. So this is crucial if we want to create, for example, if we want to create manufacturing in hospital. So we can do this self-manufacturing, but first things we need to get is this license, good manufacturing practices. And also we also need something like an ISO standard. For example, ISO 13485. This is specific for this. Right. So here I mentioned about this is Medical Device Innovation Center in National Cheng University. We focusing on this medical device development, which means that we will encounter. Sorry, there's some noisy. I hope it won't bother you. But so Medical Device Innovation Center (NDIC) we have this ISO standard, so that basically once we started a project, we can be able to accelerate the process to the market. So this is the reason we want to obtain, and we are the first Taiwan medical institute obtain this standard. So just to give you a brief idea, and so in 2018, actually, I just mentioned about that in the beginning, the regulation is not very clear, so that even though we have some applications, we started to manufacture it, we started to produce it. However, we can't actually apply, and also we can't actually to sell the product. 2018, this is actually this was actually a work we in the SKU also joined to make this guidance. So first we mentioned about this guidance for the specific for the additive manufacturing, which is 3D printing and medical devices. To manage this additive manufacturing the process, we developed a term which is a pre-established device specification. This is just mentioned about that previously there are some other process, there are some other methods you try to manufacture the medical device. So additive manufacturing, just one of these kind of methods. So there's nothing changed about this device specification. So it's always follow the standard, but just the process is different. So once we clarify this pre-established device specification, so we just mentioned about that. However, you have a new device, which we call it new, is because the process you use additive manufacturing, it's just follow the same regulation requirement and the submission expectations. Okay, so there will be no exemption, but you just
background noise आ रहा है।
just need to follow the same regulation. So this is the current situation. Okay, this is the current situation in Taiwan. How is the 3D printed medical device should be governed. So in terms of this, I show there is an approach for research and the design and the manufacturing, and also for the clinical clinicians. So this approach we keep in mind will be possible to accelerate all this process, development process, and so this information provided here is for any collaboration, so that we be able to work together. So if any of this our distinguished guests that you would like to have this cooperation, just keep in mind so that in Taiwan now we have this 3D printed medical device guidance, so that you basically if we would like to have some for example some new devices, new tests, so basically we just bring all of these tests. So that's because of this this regulation has been clarified, so that recently we have more this kind of products come out, and now they are also under the clinical trial, either on clinical trial or some of them to use. For example, on top, this is the E3. E3 is one of our the development institute. Okay, so this institute they have this facility and to manufacture some of this method printing, and so this is for the dental the dental application. And NADAP, which is they produce some of the, they also have the very very good quality controlled lab, so that they started to produce some of these kind of the knee joint and also the knee joint this top here. So this is almost like the so that they need bigger and much machine. Some for the dental, and like for example, the crown, they have using some this ceramic material. So this from the collection, they used to provide this this kind of operation. Right now, they're also focusing on medical patients. So these crowns here, they made by the ceramic printing. Okay. So here we just mentioning about how and here. The part here, I'm going to tell you kind of implementation in NCKU and the NCKU hospital. So first, we the Institute of the Center Medical Devices Innovation Center, we have some specific cooperations. For example, we have some dental applications here. We provide the dental department some model, crown, surgical guide, and the clear aligner. Also for the plastic surgery, sometimes we provide the model for surgical planning, patient engagement, assist devices, and also for the occupational therapy. Most of them is used for this kind of assist device for rehabilitation. This is a very common use and design and manufacturing in our center in the lab. And we also have some other, for example, also we also have in some this kind of cup knee joint models for surgical planning, and also for emergency medicine. Especially this year, we have this kind of a difficulty. So we provided some assistive device, also some other protective equipment, and during this COVID-19, and also for the cardiac surgery, it's the same. We provided some these models, models for surgical planning, patient engagement, assistive device. So most of them, they are found actually in our university. However, I just mentioned about this maker is unless we got this GMP certificate, otherwise we can only have this ISO standard. We have what we want to produce and put that into the product, final product, put that into the patient. We have the GMP. I started to show some of these examples in our lab. So first is a picture of a digital dentistry. So we create this manufacturing line. First, we started from the scan, and then we started to scan the teeth and some oral these models here. So we can be able to get this digital model. So once we get a digital model, and we can start, we do the reconstruction, and we started to design and modify it. So once we got to the design, we can start to do this as a manufacturer. And we used to use in this kind of CNC computer numerical control this machine. So we use this substrate this manufacturing. However, we also have this 3D printing machine in the lab, so that we be able to produce some of these like a surgical guide or this kind of dental crown. Some of these like dentures. But the problem is that once we get these models and how we are going to verify it. So this is another issue, and it came out, and also it came out to from our Ministry of Science and Ministry of Health and Welfare. So later on, I will mention about this part. So they just want to check how precise of your processes, how precise of your design, your surgical guide. So that's another part. So this is a picture of the lab. So basically, we have these dental technicians. They work in the lab, and so the machine here. So they're using some of this software to design the crown. Some of them now they started to work outside the company, dental company. But in the beginning, all the process is we get the orders from the clinician. So once we get the order, it's sent out to the lab, and we started to design. And once we finish the reconstruction, design, or modification process, we send that into the manufacturing line. So basically, we try to provide a not necessarily to be on site. It's actually could be the crowd. Okay, so which means that we be able to collaborate with our international partners, so that we don't necessarily to be always on site. So the beauty of this digital technology is actually we rely on Wi-Fi and the digital files as well. So just like the digital dentistry, here I provide another, I demonstrated another solution here. So this is for most common department in our hospital. So we can have your medical image from the CT, okay, from the MRI, and the reconstruction in our center. And once we done this reconstruction and we started to design and we found which part and we selected the right tools, and you can get your part. We just mentioned about that once we finish this printing, we need to verify it. And so this is the important thing here is that we be able to how to show that this print is actually, for example, if we print okay, if we print a Mac, okay, so how are we going to verify this? Okay, so later on we were going to show that how we the skills. Okay, so anyway, currently this research all this process here and all this work here is mainly for the research and the patient engagement purpose more often. So which means that nothing is really try to implement into it. So the current procedure of the 3D printed order is requested by a clinician, and the associated cost can be covered either by research grant or self-fund. Okay, so this is about how people most of the time people will ask about how the patient can pay and how the hospital they can charge. Okay, so now this is the status that the current the cost associated cost is covered by the research grant or self-fund. So patient they can pay for that if they would like to use this method. Okay, that would be improve their experience. Okay, so this is another example of this dental application, which is we started to design some of these orthodontist models so that in different stage they could have different make a different clear aligner. So in this case, we show that the stage 1 and stage 5, so that basically we design each stage, and then in the lab we will provide our dental department the state of this aligner. Okay, so this is kind of the procedure we produce. We produce these models. However, during the time we will be asked how precise of these models. So first, the question here is how we're going to verify this. So for example, I give you the two studies here. The first study we measure how precise of this crown. So each of them are less than this crown we 3D print. It's less than 0.05 millimeter. Okay, so which means that this is about like 50 is micron. So which is this is acceptable. And the other case, which is the mesh, okay, we print out and we also ask our lab to measure that. Okay, so basically once we have done all this print and before we send that to the clinicians, okay, send me back to the clinicians, we will measure it and we will verify it. So just make sure that. The other issue though, 3D print, and most of the time we will ask about the time consuming. So this is one of the issues we started. I started this study in my department. In my lab, so that we will be able to see that how the time charge and in the machine. So we started to modify this printer, and then we'll be able to save some of the time, and basically we save almost half of time, so that we'll be able to improve the efficiency. Okay, so this is one of my work and be patented and published. Okay. So we have also done this kind of a verification, verification and for this batch test. So we print several times. Once we get this job, so we print, and then afterwards we do this verification and we put that all together. And we notice that, well, sometimes we have this distortion here, and sometimes we have a distortion at some specific areas, but not always that. So if we consider normally we use this bug compensation, try to improve these errors, and so however, we won't be able to do that. So now I have a ongoing project which is using we call it grade prediction, and we try to do is try to fix the local, and so we be able to using the software try to compensate it beforehand. Okay, so basically this is possible in this polymer printing. However, I think metal printing is also one of these important because they will all, sometimes they have this kind of mechanical problems, heat, thermal problems. So, for example, so that we be able to do that beforehand, so that is quite important. So we just mentioned about this verification. However, I think the other work we have done in SKU is education and transformer. Okay, so this is a workshop in 2019. I delivered later in Vietnam in UMP, University of Medicine and Pharmacy, Ho Chi Minh City. So because they have some these students from their school, so that we started to teach them how to do that, so they can design their own work. So once they have some ideas, I show some of this software, and they can start to use, and they can do the design by their own. Okay, so in the end, we can see that the right-hand side here, there is the baby these processors that they basically this is an assisted device for them to use it. Some more examples, but I think the most of the part is when we started to look at the more complex cases or more complex, complicated purpose, such as in the area of cardiac surgery. So I also invited to the discussion, and we started to do some of this kind of reconstruction, and we realized that, well, the surgeons, they won't have that much time, and the clinicians, they won't have that much time. So we have to get someone and to provide the right area we want to make, and we want to look at that, and that's for example, for the surgical planning purpose. Okay, so this is very important that we need engineers. We also need clinicians. We need the domain knowledge, so that I look at that, and we discuss with some of these surgeons. Of course, we can do that by our own, but I think the most important is how to get this education, more properly, and we also look at these regulations, because once these complicated cases, if they're going to be, in practice, and most of the time we just focus on one case, but if these cases has been many cases, and they become the regular cases, so this is very important issues I look at that. So that's the reason that drive me, the motivation that drive me to the school, to the department. Now I started to teach students, because I'm looking at that. I look at the situation. I found out that well, the engineers, okay, they don't have that kind of communication skills, so that not much. They don't have that much communication skills with surgeons, so that it's better if we do that from the undergraduate. Okay, so we started to do some project-based learning, so that basically I try to develop this kind of lab. Okay, so the third part here, just mention about what kind of facilities in NCKU. So please use some of these ideas, what kind of equipment we normally use. But of course, not kind of not only this brand in our hospital or in our university, but just give you some sort of idea. So FDM, which is a field deposition manufacturing, which is most common use in the models printing and to create or to get some ideas down, so that the FDM is actually quite cheap to use it. SLA and the DLP, which is also have a very good features of the smooth surface, so that we use it especially in dental applications or in some of these microchip. Okay, so we have some ongoing projects. We are doing some microchip okay, to do the or the DNA test or something. We also have some equipment, for example, the polyjet. They can have in some quick and mass production. And we also have this metal printer. One equipment is from the Renaissance. We have some local Taiwanese brand. Okay, so this is for the metal printing. Later on, I will also introduce you. Recently, I have started to get this kind of printing using some silicone rubber material. So this is FAM, which is a fluid additive manufacturing. So fluid additive manufacturing, you can see that the material itself. Okay, so if you look at the machine here, you can see there are two tubes here inside there. So they are the fluid. They are basically the silicon fluid, silicon liquid. They started to print. Once they started to print, for example, if you look at the left-hand side, down-hand side, you can see that there's a short insert. Okay, so this is short insert, short part. So this short part they start to print. They keep the silicon properties, so it's soft. So you can increase some of the hardness as a localized hardness. It's possible also to print some of these mimetic this material. So you can see the left and the top side of this print product here. This is for specific for this like a suture. Okay, so for the suture, they can have this kind of a practice model. Okay, so this is a company is called St. George. It's also a Taiwanese brand, and this is from the alumni from the SKU alumni. They founded this. They created this company. Okay, so basically this is quite interesting material, because if we use the FDM, won't be able to inject that much liquid. Okay, so this is basically liquid printing. Okay, my last piece of plan is going to talk about some of these case studies. You won't take that much time. Going to show you is the project, this kind of a case, the project here. The first case is plastic surgery. We done this project is during the time this patient they have they need to fill in mandibular. Okay, so there's a part they already try to fix it. So they start to use their okay, the bone. Okay, they could after that. Okay. So what happened is that the surgeons they have this data, they have the CD data. So they provide the CD data to us, and then we started to reconstruct the model, and then we started to find out what's the best angle for them. Okay, so basically we talked to the students, and they said that normally they take this out and the bone out, and then they were going to measure that, and they were started to cut. But they will take a time because they need to watch where they're going to cut it, and so normally it will take like many hours. And so that's kind of a procedure they won't be able to, accelerate it unless they are very experienced. So here we provided it is this surgical planning. It's a purpose for surgical planning, and this case can also provide the patient a clear understanding about how the manipulator can be performed. Okay, so this is one of this purpose is what we just mentioned about how to engage with the patient, and they can have a better understanding before they go into this surgery. Okay, so okay, the second case is we talk about again, it's also the plastic surgery. This case is provide the patient an understanding of how this tumor. So if we look at that, they have a finger tumor here. So this tumor already start to develop the finger bone. So when I look at this CT scan, they found out that there was a cavity inside them. So the surgeons, they would like to fit in some of these cracks to the cavity, so that this is basically better understanding for the patient, so that they can give that this idea how this surgery this surgery is going to do. Okay, so basically we get this kind of request. Sometimes we get this request and we have to ask. For example, this case, we have to preparation time is less than a day, and the preparation time is less than an hour. So once we get these cases, we have to do that as soon as possible. Yeah, but we'll be able to do that unless we get this manufacturing in the hospital or in the university. Yeah. So I try to summarize why I talk about my talk today. First, I will talk about the current situation in Taiwan. So the guidance for the management of additive manufacturing medical device can be referred to our TFDA, and this can accelerate the entire research time to final product. Okay, so this gives you some of the ideas how if we're going to get together in the future time, we can follow some of these, these considerations. And the second, we I've just demonstrated some of these our hospital manufacturing procedure. So normally we get that a request from the hospital and from the clinician, and then we start to design and we get back to them. And the cost, how we're going to manage the cost. Okay, so but the issue here is actually training the engineer. I mean, how to train the engineers with field of communication, and they can be able to have that kind of domain knowledge, so which is quite urgent. Okay, this is quite urgent. And last part, we talk about the 3D print models. Okay, they can provide some of these patient engagement. Okay, so they have given them a better idea what they are going to do and what happened in their surgery. Okay, so a good practice can also shorten the duration time. Okay, so they can basically to improve that this efficiency and also to reduce this body the recovery time. Okay. So okay, that's almost my talk today, and if any questions, I'm very happy to answer that, or otherwise I can reply by email. Okay, thank you very much. Thank you for your attention.
Thank you very much for such nice talk.
Thank you.
And excellent, you have presented case studies also. So if any queries are there by participants, please write in the text box so that we can ask the speaker. one query is, can you please tell about FAM?
Okay, so FAM is actually I just refer to fluid additive manufacturing. Okay, so you can, if you look at this machine here, sorry, go back to the slide. Thank you.
Ready ആയിച്ചാ? Okay, okay. நான் இன்னைக்கு வந்து வாங்கிக்கிறேன்.
Yes. So you can see here, the right-hand side here, there's a machine, and normally we use this polymer so that there's wires going to there, and we need to heat it. But instead, we're using this liquid. So if you look at the left-hand side, it's quite similar to the idea about this cell printing. So basically, we provide this liquid, this is silicon liquid, and on the part, so that once we print, and you will cure it. Okay, you will cure it. It's also heated by the heat, but sorry, cured by heat, but it's not really like a solid filament. Okay. So this is basically this print. Once you print out, you can see that this is a silicon dropper. Okay.
The next question is, what is the temperature used?
Okay. You mean that this pen?
Yes.
Okay. I'm not quite sure about the temperature right now, but I can answer that questions by email you. Okay. So I can go back and check it.
Okay.
But also see that if you need more information, that I provided a link there. But normally you can see it's rubber the temperature. Okay. So you won't go to burn it.
There is one more query. Can you explain how do you design something after getting information from clinicians? And what type of information you can get from doctor for designing?
Okay. I think this is a good question. First, I've encountered some many different cases, so that sometimes this kind of information is different. For example, some clinicians, they just got a very broad idea. They want to do something not kind of existing product. So sometimes it's very difficult to just do that in very short time. But most of the case, for example, I just mentioned about some of the procedures we have done. So first, we need the medical image. So we started to get this kind of image where we can get that from. If that's a CT scanner or if it's from the MRI, then we started to do that, ask them to they can just transfer the data to the cloud. Okay. So what kind of information we get that from the doctors for design? It's basically we will ask the doctors what the purpose is. For example, in my case, in the beginning, I just think this is for the surgical planning. So basically, they just want this kind of the model screen and be able to explain to the patients. However, sometimes the doctors they would like to know what kind of they connect get a further design for the joint cut or for some assisted devices so during their surgery. So this is also possible that during the discussion that we can get. Okay, so the more more solid idea they can provide, and we can think about what kind of equipment we can design.
Okay, there is one more distinct query from Tuhin Mukherjee. Can you please explain the second case study once again? Probably he wants to ask you something.
Right, okay. My second case study shown here is basically there's a tumor on the finger bone, and so they try to remove that tumor and to fit in the cavity. So the purpose of this is they want to know how big of that cavity. Of course, that possibly you can also measure that from the software, but they also want to show the patient. So this is actually patient engagement case because they want to have in the whole hand model, and so that be able to explain to the patient why they need this surgery and how big, how urgent they need to be done. Because when I look at the cases, the bone almost erodes. Okay, so it's a very, very big inside there. Okay, so that's the second case.
So thank you so much. I don't see any other queries here. So please go ahead.
Okay, thank you so much, Dr. Yu. Now we're going to
Yeah.
have the second speaker of today, Dr. Prabhat Chaudhary. Dr. Prabhat Kumar Chaudhary is presently working as an associate professor and head in the Division of Orthodontics and Facial Orthopedics Center for Dental Education and Research. His main clinical thrust areas are orthodontics, orthodontic management of cleft lip and palate, removable appliances. His main research interests are caries risk assessment and tissues regeneration in cleft lip and palliate patients 3D printing in orthodontics and procedures that shorten orthodontics treatment duration, clinical innovation and simplification of orthodontics treatment as per need of Indian subcontinent. He has several publications in reputed journals and handling several projects from the government of India. Now I would like to welcome Dr. Prabhat Chaudhary to present his speech on the title 3D Printing Technology in Oral Health Science and its Clinical Applications.
Thank you so much for your kind introduction. Am I audible and my screen is visible?
Yes, you are audible and screen is visible.
Okay, thank you. Good morning to all of you. It was a very wonderful lecture by my friend Dr. Yusen Lin from the National Cheng Kung University Hospital, Taiwan. And we learn from each other a lot regarding 3D printing and its dental and orthodontic application. Today, I am here with the objective to discuss the 3D printing applications in oral health science and emerging opportunities of the in collaborative innovations to solve the unmet clinical needs. So this is the outline of my presentation. First, I will give a brief introduction of oral health science, then the digital dentistry and our experience at the CDR, AIMS, and what is 3D printing, commonly used 3D printers for dental application, and specific application of 3D printing in oral health science, and some of them has been already discussed with Dr. Lin. And other collaborative research opportunities of the 3D printing and it's to solve the unmet clinical needs. Before coming to my presentation, I would like to read disclosure. Neither I nor any member of my family have a financial arrangement or affiliation with any corporate organization offering financial support or grant monies for this presentation, nor do I have a financial interest in any commercial product or services I will discuss in this presentation. So I work here in Center for Dental Education and Research, All India Institute of Medical Sciences, New Delhi, which is the WHO Collaborating Center for Oral Health Promotion, and Cochrane Oral Health Group Alliance partner of the Cochrane Group, and National Center of Excellence for the implementation of National Oral Health Program by the Ministry of Health and Family Welfare, Government of India. At the Center for Dental Education and Research, we have we have clinical services to all the major discipline of the dentistry, and we have the master courses in 5 discipline, and we also have the PhD and the BSc courses in dental operating room assistance and dental hygiene program. So basically, this slide is showing the problem we address at our orthodontic division. So we provide the solutions to irregular teeth and solutions to dentofacial deformity, and basically patient adolescent patient and cleft lip patient and patient with the craniofacial deformity and working adult visit to us for their improvement in the dentofacial aesthetic and smile. So we provide the solution of the metal brushes, fixed one, and the ceramic brushes, some kind of removable appliances, some kind of myofunctional appliances, and some kind of therapy to the cleft lip and palate and patient with the craniofacial deformity. If we see the user charges, our department is it's around 14 US dollar for comprehensive fixed orthodontic appliance therapy. For the functional and removal appliances therapy, it ranges from 3.5 to $7. Which other Indian hospital they charge around 500 to $1,200, and in developed countries the user charges is around 2,000 to 4,000 US dollar for this same treatment. We are thankful to our administration, AIMS, and the Ministry of Health and Family Welfare for providing all kind of the to provide these services to the citizen as the very nominal user cost. So, for a more complex deformity, we collaborate with our division of microfacial surgery for the dentofacial deformity, and for our plastic surgery division and other multidisciplinary approach for the care of cleft and craniofacial deformity. We also offer the high quality postgraduate education, and this one is our postgraduate laboratory, and now we have started the experimentation with the digital technology and 3D printing. So this is the our digitization laboratory, which is in our division. So here we have a desktop scanner, and this one is the CBCT monitor, which provide the skeletal data of the dentofacial region, and this is the Dolphin software, which is used for the planning of the surgical and non-surgical orthodontic and maxillofacial surgical cases. And we also have Mimix Innovation Suite, and this is our 3D printer. Most of the data from today's presentation I have generated from this laboratory only. So now coming to the to the traditional digital workflow. In the traditional workflow in dentistry, it is very labor intensive and lots of the manual work involved. In which, for example, we take a Alginate impression of the teeth and jaw, and then a plaster model is stored, and then we send this plaster model to the laboratory, and where technician design the appliances and he finish it, and then the technician send the appliance to the clinic. If you are in a university hospital, then you may have a in-house laboratory facility, otherwise you have to outsource it. What happen in digital technology? In digital technology, we just scan the dental model or hourly the dentofacial structure, and we design the appliances using computer-aided design, and then we can 3D print the model, or we can 3D print the appliance depending upon the utility, and then it can be used for clinical care. So digital technology is less time consuming and very efficient one. If we see what are the basic pillars of the digital workflow in dentistry, then there are three main pillars of the digital workflow in dentistry, or in general in any specialty. Number one is 3D imaging. 3D imaging is very important because this is the baseline data we need to acquire through the 3D imaging. It can be a surface scanning, or it can be a invasive one, X-ray, CBCT, or a normal CT. Then from this baseline data, which is in STL file format or any other format, we design the appliances, we design the changes, artificial simulation we do using the specific computer aided design for the different discipline and different application. But Mimic Suite we can use for most of them. And then after that, this computer aided design software, they provide the STL file format that can be fed to the our 3D printer, and it provide the object in the real form. So if we see what are the modalities of the image acquisition or baseline data acquisition in dentistry, there is two type of the imaging modalities. One is invasive one and another is non-invasive one. Invasive one is basically the CBCT or conventional CT, and non-invasive in may be classified as a direct method in which there is a intraoral scanning, in which we directly acquire the data from the patient mouth. Either is benchtop or desktop scanner through which we get the data from by the scanning of the dental model in a desktop scanner like here. And another is the extra facial scanner, and this provide the data of the face instantly in around 1.5 millisecond of the 3D data of the face they provide. So if we see the various kind of desktop scanner for the dental application, here we can see three major companies globally. They produce the desktop scanner for dental application. These are the Ortho Insight 3D Motion View, 3Shape scanners, and Mastro 3D scanner. This is Mastro 3D scanner we have in our department, and most of the work currently we do by using this Mastro 3D scanner. And if we see what is the basic principle of this desktop scanner, it is that they having a laser light source. This laser light source illuminate the object, and then they are having multiple cameras, and this multiple cameras capture the data of any physical object or dental model, and then specifically design algorithm. They convert this data into the STL file format. These are the various kind of the commercially available desktop scanner for dental and oral health science application, but most of the desktop scanner are based on the laser light, and they have accuracy of the 10 to 200 micron, and the scanning time is ranges from the 2 to 10 minutes, and they have a specific computer aided design software like 3Shape having Ortho Analyzer, or any other dental application. They are having different software, and Mastro having Ortho Studio. We use basically the Ortho Studio, and the Ortho Insight they having Ortho Insight software. Here I would like to share with you some of the our experience for the 3D scanning at the AIMS. So here in this video you can see the scanning of the dental model using the Mastro desktop scanner. Basically it takes around 3 minutes, but this is a little with faster motion. So this scanner can be used to create the digital model of the teeth and associated structure. So in this we get the patient data from the plaster model to digital model in this manner, and this in the STL file format. We can save it and we can use it for the printing. So I reviewed some of the literature for the what is the current status of the digital model in dentistry and orthodontics, and literature suggests that digital model as reliable as to traditional model with high accuracy, reliability, and reproducibility. So we can use digital model for the clinical application in the treatment planning and the education of our resident. So now we have learned till the creation of the STL file by using desktop scanners. Another method of the scanning is the intraoral scanning. This is the more convenient because we can create the 3D data directly from the patient mouth. And this intraoral scanner, they have a two part. One is the computer monitor to enter the prescription, approve the scan, and review the digital file, and another is handheld camera band which go inside the mouth and record the 3D data. There is basically three basic type of the intraoral scanner, and the basic principle is only three basic one. Number one is optical triangulation. Number two is parallel cone focal imaging, and number three is 3D in motion video. Based on these three technology, various kind of intraoral scanners are used for the dental application. But what is the basic principle of all these scanner is that they have a energy source in the form of laser light or white light. And this laser light from here, this camera band, this illuminate the object, and then light is reflected from the target to surface, and it is sensed by a specifically designed sensor in this camera band or a camera, and then a specifically designed algorithm convert this energy into the digital data, and then it can be saved in the STL format. So these are the various kind of the intraoral scanner available for the clinical application. Most of intraoral application, they provide output in open STL format, and scanning time ranges from 5 to 10 minutes. The last one, the imaging modality I would like to discuss is the face scanner. This is digital stereo photogrammetry technology. And this scan the whole face in 1.5 milliseconds. That is very fast. See the 3D data. So now coming to the our topic, 3D printing. When I teach my resident what is 3D printing, I always tell them 3D printing printer are the robot. And I teach my resident in the manner that you all are familiar with the desktop printer. Desktop printer is used for the printing in X and Y direction. That means left and right, and the top to bottom direction of the A4 size paper. But what happened in 3D? There is a Z direction. In that means there is a height. So 3D printing involves the printing in all the three plane of the space, X, Y, and Z direction. And most of the dental professional, they are familiar with the subtractive manufacturing, in which a block of the material is carved to form an object, just like the CEREC restoration. But what happened in 3D printing? A sequential layer of the material is deposited on the top of one another to form an object. There are basically, these are a main 3D printing technology for dental and oral health application. And my friend Dr. Nishalin already has been discussed about this technology. Number one is stereolithography. Number two is polyjet photopolymerization. Number three is digital light processing. And number four is fused deposition modeling. To discuss about each of this technology is beyond the scope of this lecture, but for the better understanding, I will discuss about the SLA technology so that it may provide an overview of the 3D printing technology. This is the computer monitor, and this monitor is attached through this 3D printer, and this is the ultraviolet light source. This is the CAD model which are going to print in this animation. And this is the platform which will move down when to accommodate the printed layer, and this is the polymer liquid. Okay, now printing of the CAD model is started. So when first layer is printed, this model goes down, and again this platform will go down, and to accommodate the another layer in this manner, it will accommodate the whole 3D printed layer. This is the final CAD model, which is similar to our initial CAD model. these are the various kind of the global companies, and they produce 3D printer for dental and oral health application. Most common one is still on the SLA technology is Form 2. Form 2, the company has been discontinued. Now they are producing Form 3 and Form 3B for biomedical application. These are the low cost printer and for small sizes offices, our laboratory. And another one is based on polyjet technology, that is Object 30 Autodesk. In our department, we are having Object 30 Autodesk, but this kind of printer are little bit costly, and they are specifically useful for medium sized offices, university based practices, and large laboratory. And another one is based on digital light processing. These are the Envision Tech printers, and they are in between the cost between the Formlab and Object 30. So this is the final process of the 3D printing in field. First step is acquisition of the data, then followed by creation of the STL file, and then preparation of the model for the printing, and followed by printing post processing. I also reviewed the literature regarding the what is the current status of the 3D printed object or 3D printed model in dentistry, and current literature suggests that dental model reconstructed by rapid prototyping technique are considered clinically acceptable in terms of accuracy and reproducibility. So these are the various kind of the current application of the 3D printing in the dentistry and orthodontics. And the first application in orthodontics for the preparation of orthodontic models are appliances. Another is in clear aligner. Another application in crown and bridge, and another application in implant and surgical guide. And some of them has been already discussed with my friend Dr. Yushen Lin. So the first application I would like to discuss is application in the orthodontics. And these are 3D printed study model that I have already discussed, and 3D printed surgical guide and ancillaries, and the feeding 3D printing for the feeding appliances, making aligner and customization of orthodontic applications using 3D printing. I will discuss these two. One is customized appliances, and another is the aligner. So this is the traditional way of liner therapy, which we do in our department. Here we take impression of the patient jaw. This is the impression of the patient jaw. Through this impression, we create a dental model, and this model is manually cut. We cut each teeth manually, and then we do setup in the backs here, followed by a minor movement using the semi-automated software, which is known as a clear aligner software. So we movement in the range of 0.25 to 0.5 millimeter using this software. Then after that we fix it, we seal it, and we go for the thermoforming using thermoforming sheets to make the aligner. Using this, we deliver this aligner to the patient. This is a very labor-intensive process. But with technology, here directly we get the digital either by intraoral scan or desktop scanner. Then we do the setup and followed by we do segmentation and virtual planning in which different stages tracked virtually. Then we go for 3D printing of these models, then followed by thermoforming of the aligner, and we deliver it to the patient. So in case study, I would like to show you with the aligner therapy. Here you can see the space, and this is minor relapse case. So we use 6 aligner set, the range of 0.25 millimeter tooth movement with aligner, and finally closure of the space. Another application of 3D printing is in the production of the customized braces. So for the customized braces, this is very important because some adult patients, they don't want to have labial orthodontic appliances, so they want the appliances that is not visible in the mouth. So the researcher, they worked for the development of the customized CAD/CAM appliance. This appliance is developed in the goal. So accurate precision and accuracy is very important for this appliance. So after the 3D scanning in laboratory using computer, the appliance is designed, and then it is 3D printed in the BEX model, and followed by this appliance in the goal. I'd like to show another case study using this lingual appliances. Here you can see irregularity, and with this lingual appliance, there is a correction of the irregularity of the teeth. And beauty of this appliance is that it is not visible from outside, whether it is undergoing or untouched. Another application of 3D printing is in making crown in bricks. So this 3D printing can be used for making of the crown and bridge application. Another application of the 3D printing is surgical guides. So we can use the 3D printer for making surgical guides, in which we need a 3D of the dentofacial skeleton. So followed by the this data is segmented, and we record the osteotomy set, which our surgeon is going to do osteotomy in the OT table. This is the 3D model of the Okay, so this is 3D visualization of the situation after the required anterior movement. Then import an adjustment of the virtual model, followed by adjustment of the lower jaw. Here you can see, and then this one is the virtual blind splint. It is placed between the upper and lower teeth, and followed by this splint is digitally designed, and this splint can be 3D printed using biocompatible materials available with these printers, and then it can be used during the surgery, and it will be in mouth for a long period till the stabilization is there. So another application is in the mock surgery, because in this case there is a lots of dentofacial deformity and facial asymmetry. So 3D printing provided the accurate position of the bone, and where is the exact problem. So in this way, this is actual model. This one is after mock surgery. It is very good tool for the patient education and for the education of the resident doctors. That means our post training. The last,
We request everyone to please mute themselves. Please mute yourself.
and they have found that 3D printed plants survive 50 years in 95. So based on data from this research, 3D printed implant is the reality. Finally, I would like to discuss some of the collaborative opportunities with the participant and the expert here. Number one is development of 3D printed orthodontic appliances. Number two, application of 3D printing in craniofacial tissue regeneration. And number three is the development of 3D printed clear biocompatible material for aligner therapy. This is the traditional way of appliance therapy in our specialty, that means in orthodontics, in which we take an impression of the teeth and associated dental-alveolar structure, and we get on which we do some kind of bending, and we create a plans like this. I would like to collaborate with the other researchers here because now because with the availability of this 3D scanning and the computer-aided design, some researchers around the globe, they have started experimenting with the designing of such kind of appliance and 3D metal printing. But problem is this: for a university-based clinical practice, we cannot afford a 3D metal printer because cost is high. So I would like to invite the the participant and other speakers are academia person here are from the industry. We can collaborate in this area to design and develop the 3D printed metal appliances. In this slide, you can see the digital planning and 3D printing data was provided by my friend, the CEO of the CA Digital in Germany. Basically, one of my friend from Switzerland, he is most of the paper on the 3D printed metal appliances is from that researcher, Dr. Simon Clark. He is a private practitioner. But during discussion, he told me that he is not having a 3D printer. He is using the facility of the CA from the Switzerland, sending the appliance. They are sending to the Germany, and then this German lab is sending the printed appliance to the to the but this is not possible because cost is very high, and affordability would not be for our patient for such kind of a plan to develop some kind of solutions that be cost effective also. Another application is production of the customized bracket. This was the first paper by the German researcher Carl Friedrich Kreh. He published this paper as a proof of concept for 3D printed orthodontic bracket in 2016. So Kreh demonstrated first report that 3D printed bracket is reality. So I also want to work in this area in collaboration with biomedical specialists to develop some kind of the 3D printed appliances.
7708.
Another application.
69923.
Okay. I would like to discuss having 3D printing in tissue engineering. As we all know, tissue engineering tried has been three things. One is the scaffold, that means collagen, bone mineral, and some synthetic material. Cells basically is and molecules like BMP and platelet-derived growth factor. With the time, when all this applied together and with the appropriate environment like vascular supply, there is a regeneration of the tissue or any of the organ. I would like to collaborate with the researchers in the area of the periodontal and tissue regeneration. This was the very first report for the osseous regeneration using the 3D printed scaffold was published by the researchers from the University of the Milan from the Italy and the University of the Michigan, USA, in one of the top-rated dental journal in 2015. They have this is here you can see lots of the different bone loss and periodontal defect, and this is the CT data. From this CT data, they have created a scaffold, and they printed this scaffold in prolactone using Formiga P100 machine EOS base, and then after that they have grafted it and they got a very good result for 1 year. But later on, this was a failure, but it was also even after the failure, it published in top-rated journal because this was the beginning of the application of the 3D printed scaffold for human studies for the craniofacial and periodontal regeneration. Basically, the Formiga P100 printer are very costly, and it is not possible to afford in a university-based practice. So Indian industry people or Indian industry partner, if are large research institution, if they are having such kind of printer from the EOS, we would like to collaborate for the development of the patient-specific implant. So another tissue regeneration application is bone grafting for the cleft lip palate, which need to be explored. You know, when cleft baby is born, and the immediate question of all the parent whether my baby is okay, because there is a lots of defect in the soft tissue and hard tissue. So hard tissue defect in the jaw, and there is a gap here, and soft tissue defect is this soft tissue defect is closed by our surgeon at the age of 3 months, and hard tissue defect is closed at the age of the 12 months. But still, after this primary surgery, there is a loss of the bone defect in the children with the cleft lip and they require secondary alveolar bone grafting at the age of 9 years. Because of this large defect, we need to take a bone from the another side. So so there is a donor side morbidity because we need to take bone from the same patient. So this is the complete procedure. There is a large defect and fistula, and then donor side from the donor side bone was taken, and it was grafted here, and finally after this surgery. So I have a proposal for cooperation by using 3D printed scaffold. The solution is that we can print a scaffold in nanohydroxyapatite or polycaprolactone, and it is seeded with the stem cell and growth factor, and then it is grafted in an animal model in artificially created cleft. If successful, then we can cooperate for the development of such kind of therapy for human also. The last idea I would like to discuss is development of the 3D printable biocompatible material for aligner therapy. Here, this is the traditional way of aligner therapy which we are using in our department also, in which we do desktop. We have desktop scanning, and then we do planning using our Artho Studio software, and then we do 3D printing and followed by thermoforming. All the major company are anyone in the world using the same technology for the aligner production. But the problem is that being in a government hospital, our user charges is very less, and it is also very labor intensive work. So we thought to develop a system which can be based on directly on the 3D printing of the aligners. There is no need to print the model, and then no need to thermoform on that model. Directly we can print the 3D printed model. And in this idea I have also published in the Journal of Aligner Orthodontics as a future of aligner orthodontics in digital age. So I'd like to cooperate with researchers to develop a biocompatible 3D printed material for aligner application. So in last, if we see what is the 3D printing market in dentistry, Smart Tech report suggests that 3D printing in dental market may reach around 3.1 billion by 2010, 2020, maybe a little bit less due to COVID crisis. But looking into the future for dentistry, the report predicts that 3D printing technology will reach more than 60% of overall dental production in the next 10 years, and perhaps even higher in certain area. I would like to share one experience when I visited to in 2016, and I met with Dr. Yusen Lin, our previous speaker. At that time, we were not using any kind of 3D printing in our department, but now at least we are using in many areas 3D printing within the 4 year of the time frame. Keeping in mind of this change in paradigm shift from the conventional to the digital technology, and working in the AIMS, working in a public hospital, most important challenge for us at AIMS is not the integration of digital technology, but to develop the cost-effective solutions for day-to-day patient care. So I would like to invite the researchers to collaborate together, and keeping in mind of this responsibility, I have also started some of the project. Number one here, I'm showing the ICMR funded project to evaluate the effect of scanning technology and print layer heights and the accuracy of three-dimensional printed models, and another for the aligner therapy Department of Science and Technology India Taiwan project for the automatic diagnosis and monitoring of orthodontic invisible appliance cases using artificial neural network. So in summary, I would like to summarize that clinicians have many unmet clinical needs. They want to find a solution, but they are not able to find the solution because they don't have expertise in biomedical engineering. So by joining the hand together, clinician and biomedical engineers, we may find a solutions of the unmet clinical need by the collaborative innovations. So I would like to end my this presentation by the quote from the George Bernard Shaw: "Imagination is the beginning of the creation. You imagine what you desire, and you build what you imagine, and at last you create what you build." I would like to say George Bernard Shaw was only person among the few person, and he was the first person who won both the Nobel Prize and Oscar. Thank you so much for patientfully listening, and I'm thankful to organizer for providing.
Thank you, Dr. Prabhat, for such a wonderful talk. Thank you for sharing your experience and insights with the participants. I hope all the participants must have benefited from your talk. There are few queries from the participants. The first query is, what about material? This is from Prem Kumar. Which material are you using to print dental parts? Are the materials provided by the printer manufacturer, or there are any specific kind of properties other than currently available material you require? So this is a big question for you.
Okay, very important question. Actually, the resin material, the provided by the manufacturer for the 3D printing. Currently, we are using the object 30 statuses, so we use the material provided by them. But some material is also available, but safety is very important for 3D printed material. So if it is not critical area, we can use the open source. But it is a critical area, then I will suggest to use FDA approved material only.
The next question is, please explain the principle of desktop scanners.
Okay, that is explained, but I would like to explain again. Desktop scanner are basically they scan the dental model, and they are having two sources. One is light, and another is the camera. Multiple cameras. So laser light or white light illuminate the object, and the multiple cameras capture the object in 3D view. And then specifically designed sensor are there. They convert this data into the STL file format or 3D format. 3D format.
Next question is, what is thermoforming?
Okay. Thermoforming is a technique when by the 3D printing we get dental model, and for the tooth movement there is a aligner. It is a plastic sheet which align the tooth in the increment of 0.25 millimeter per aligner. So this aligner is fabricated by thermoforming machine. This machine I showed in my presentation, the BioStar machine we use for thermoform.
Next question is, when can we particularly use the desktop scanner?
Okay, Desktop scanner we can use for the scanning of the dental model, basically. But best is if you are having intraoral scanner, and that is the best thing. But till from last 3 years we are tendering, we are not getting the intraoral scanner. So we are outsourcing the intraoral scanner for a special purpose. But desktop scanner can be used for the scanning of the dental model. But intraoral scanner is needed.
Next, next question is from Abhishek Shetty, who asks you any pain point faced in dentistry-based 3D printing.
Can you repeat this question again?
Any pain points or any difficulties faced in dentistry-based 3D printing?
Yes. One is the many difficulty because we need to train ourselves in this area. We are a clinician, we are not a doctor. So it is not easy to get mastery in the designing and the whole process. And also we need to spend lots of time in this area from our clinical work and teaching. So these are the difficulty. Other than the cost is very high for 3D printer and intraoral scanner. Maybe we are able to afford here in the AIMS, but other hospitals they will be able to afford or not. We don't know. In complexity.
Next question is from Geeta Bala Subramani, who asks what are the materials used to generate the periodontal?
Yes, that scaffold they have used in polycaptone, PCL material, and they have used EOS Formiga P100 3D printing machine. But problem is that the Formiga P100 machine is very costly, around 6 to 7 crore. And another thing is this PCL material that they have used, it it resolves around in a year. So when it resolves in a year, that was there was a failure in that case. We need a material that should resolve within 3 to 6 months, so that it should be replaced by the bone within 3 to 6 months. So another material people suggested like gelatin or polylactic acid. So this is the area of exploration. We would like to collaborate with the many alike researchers.
Is this material biodegradable? This is the continuation of the same question.
Yes, because polycaprolactone is take PCL around 1 year, but if we are using gelatin or PLA, maybe 3 months to 6 months.
What about frequency of infections from printed implants?
Actually, that I don't. I need to check.
Then next question is which DLP material is used for implantation in case of deformation surgery for correction?
DLP material.
Yes, sir.
Actually, as far as my knowledge, DLP material, DLP is a printing technology, not a material. So it can it use different kind of material, but for the implantation, only titanium we can use, and this is by the metal printer, and it is very costly, around 6 to 7 lakh. So 6 to 7.
Next question is from Saravanan. He's asking, is it required to testing 3D printed parts in dental product?
Okay, this is very important question. So if we are using AFD approved material and already we are going to use 3D printing in already undergoing treatment modalities for conventional approach, so it is not required. But any deviation, suppose new devices or new appliances, then definitely we need to get approval.
Next question is there any material jam situation like paper jam in 2D printer?
Yes. Actually, when in 2016 to 2019, my understanding was that when I am printing one model or 10 model, it will take the amount of the material that is needed into the 10 times for printing and the 10 model. But when we started working with our 3D we found that even if we are using one model or 10 model, there is a loss of material in the printing process, which is jam in the nozzle and other areas. So whether I am printing one model or 10 model, there is a base of the material is similar. So yes, definitely, there is a no, we did not experience any jam, but there is a wastage of the material.
Next question is from Miss Mandy Mary Karbangar. She is asking, is customized bracket and arc wire different from individual to individual?
Actually, customized lingual appliances are different for individual to individual. And Dr. Bickman, he was, I think, a German researcher. He introduced this technology. And cost is they produce these appliances in the gold, and cost is around 1.5 to 2 lakh. That's why some of the Indian startup also they have started producing these appliances in stainless steel. Yes, they are customized, and they are different for they are customized for individual base.
Next question is from Miss Navia Susan Thomas. She is asking, is there any good 3D slicing software that is compatible with Android? Any software you can suggest?
That I don't know. I'm sorry.
Okay, thank you very much, sir. Now we to have the third speaker of the day, Dr. Dinesh Bhatia. Dr. Dinesh Bhatia pursued his PhD in Biomechanics and Rehabilitation Engineering from MNIT Allahabad, India, and Master degree in Biomedical Engineering from Mumbai University. He completed his MBA Dual Specialization from IMT Ghaziabad. He is currently working as Associate Professor in the Department of Biomedical Engineering, Northeastern Hills University, Shillong, Meghalaya, India, since August 2013. He was once the Assistant Professor at the Department of Biomedical Engineering, Dinbandhu Choturam University of Science and Technology, Murthal, Haryana, India. He was selected for the Young Scientist Award broadcast by the Government of India to pursue research in osteoarthritis at Biomedical Engineering Department, Florida International University. He was selected as one of the 12 young biomedical scientists by the Indian Council of Medical Research, Government of India. He has several research papers in reputed journals, conference, seminars, and symposia with teaching and research experience of more than 17 years. He is a panel member of many scientific professional bodies, editorial boards, committees, societies, and forums. Dr. Dinesh worked on several funded projects from the Government of India, also the author of 6 books and 20 books chapter till date with more than 200 plus publications. His areas of interest are medical instrumentation, biomechanics and rehabilitation engineering, medical informatics, signal and image processing marketing, international business, and environmental sustainability. Personally, I would like to welcome Dr. Dinesh Bhatia to the platform to present his speech on the topic 3D printing applications and future prospects.
Very warm good morning and thanks for the nice introduction. So, before I start my talk, I will just like to show you some videos, and I've also included the links in my talk. Am I audible and my screen is visible to all of you?
Yes.
Yeah. Yeah. So I'll just show you some videos. And I want to show you one more video and then I continue with my talk. Okay. So now I will go with my PPT. Is my PPT visible to all of you?
Yes, Vidya.
Okay. Okay. So 3D applications and future prospects is my title of the talk. I'm working in Northeastern Hill University, Shillong, and we are located in the northeastern part of the country, and we are in Meghalaya, whose capital is Shillong, which comes in East Khasi Hill. So we are having the Northeastern Hill University, which was established in 1973 by our late Prime Minister Srimati Indira Gandhi ji, and it has been a potential A-grade, NAC-graded university, and it is having 1,200 acres, out of which 500 acres is still under forest. So it's a beautiful campus, and Shillong and Meghalaya is itself is a beautiful place. And if you have time to visit sometime, you must visit this Dancing Cloud Valley and the double-decker root bridge, which is made up of roots of the trees, and it connects, and people still use it for communicating over the river. And this is the Krang Suri Falls. So it's in Jantia Hill, and you see this water is very pure, and the people, it's believed that if you take bath in this, then you are cured of all your possible diseases and other things. Now I come to my talk, and it's been on 3D printing. As I told you, in existence since early 1980s as additive manufacturing. And this technology has grown by leaps and bounds over the years. And it is quite popular since 2000, when its importance came to limelight. And it's employed in different fields and affecting several industries. Its biggest breakthrough with immense potential to develop pharmaceutical, medical devices for personalized treatment, patient-specific drugs, equipment, and anatomical models, as you have seen in those YouTube videos. So biomedical 3D printing includes fused deposition modeling, halt, melt, extrusion of filament, stereolithography, inkjet printing, selective laser sintering. So these are the videos already I have shown you. I have included in the slide also, which will be shared with you. So talk focuses on growth, advancement, and future scope of 3D bioprinting in healthcare. And it's used to improve and develop patient-specific care with great quality customized cost, providing durability and patient ease. It allows personalized treatment employing 3D bioprinting and for anatomical replicas of patients for study before producing actual bioimprinted implants and surgical devices, producing patient-specific customized drugs, and also in dental for making braces and tooth, which already my previous speaker, Dr. Prabhat, enlightened you about. So it will be exploring the challenges and limitations that lie ahead in the adaptation of this technology for mass uses in the healthcare sector. So you see this 3D printing, as you saw, I'm showing you a slide which shows industry-wise. So whether it is in motor vehicles, it is comprising a lot in the automobiles. In consumer products, it's around 18.4. In businesses, around 11.2. In medical, it is slowly growing. It is around 9% now. In academia, also around 8.5%. Aerospace, 8.2. Government and military, 5.5, and others, 7.7. So you see, it is having a diverse scope in different industries, technology. And as you see, this 3D printing, it started in 1984 as stereolithography, then came selective laser sintering. Then in 1990s, we had fused deposition modeling. Then clinical applications for biomaterials for tissue regeneration started in the mid 1990s with 3D printing and color jet printing. Then we had the first 3D printed placebo tablets. Then 3D printed drug-loaded delivery devices came in the pharmaceuticals. Then we started in 2000s with the miniature functional kidney, and slowly it has advanced. And from 2010 onwards, it has taken much rapid steps. And bioprinting of artificial liver or prosthetic jaw, or it has for vascular bioprinting in tissue fabrication, or announcement of fully bioprinted kidney, as I showed you in one of the YouTube videos. So all this is there, and the technology also has advanced over a period of time. Different type of technologies have come, so it has grown rapidly. You know, now 3D printing technology is liquid solidification, so it is like drop by drop deposition. So object is built by droplet solidification, and stereolithography is also there, where object is built by solidification of photosensitive liquid. Then there are extrusion based systems where you have the fuse deposition modeling, where object is built by melted material solidification, and semi-solid material is used by pressure assisted syringe. So object is built by semi-solid material solidification. And then we have powder solidification. So we have the liquid, we have the powder. And in this, we have the selective laser sintering or melting. So object is built by solidification of powdered material by high energy beam, and either by drop on solid deposition. So object is built by liquid building of powdered material. So these are the different types of 3D bioprinting techniques: inkjet, extrusion, stereolithography, and laser assisted. And if you see, the solid one is the fuse deposition modeling technique. Liquid is SLA, stereolithography, and powder is selective laser sintering based, inkjet based. So we are employing thermoplastic or metal wire FDM technology. It deposits layer by layer with the help of nozzle spray. In the SLA technique, we use a vat which is packed with liquid plastic or photopolymer. It is used which produce a perforated platform on the top of tank, leaving a thin layer with the surface. And with the help of light beam, each layer is hardened or solidified, and platform is lowered to insert the next layer. In SLS technique, which is almost similar to your SLA technique, but it is employing polymer, metal, or ceramic powder instead of plastic in liquid form. And laser beam selectively sinters powdered raw material to form a thin layer. At the end of each set, the powder bed is pulled down, and layer by layer, powder is added for laser sintering. So these are the different types of techniques which are there, which I just wanted to share with you. So, as already told by previous speakers, we have this material development. We develop the 3D CAD model. We have the STL file. From there, slice layers are this thing prepared, and then it goes into the 3D printed, and we get the final 3D objects. We are having the material development first, then design, modeling, and simulation, then material processing and layering, and finally we get the final product. So this is in 3D bioprinting. This is from Altum Technologies. I'm using this as a source. So DICOM data is taken from the patient, and we develop the models file. Each segment is a different STL file. So segmented image is merged into an assay, and then material assignment to each segment. Then it is going to the 3D printer, and we get the final print of the organ which we want, and that can be used for implantation. Then these are the 3D printing in different applications, whether it is human heart, whether it is brain, whether it is dental products, or any kind of tissue development. So all these different applications are there for 3D printing. So now, what is the future for 3D printing in healthcare? Where my talk will focus on. I just wanted to give you an overview and come to my talk. So there is a growing impact of 3D printing, and it is encouraging the clinicians to for its uses in the healthcare domain. And it is as per a study done by Vision Grain, it is found that this market doubled in 5 years. It was around 1.2 billion in 2013, which approximately became 4 billion in 2018. And the possible reason for this tremendous growth is due to widespread awareness and use of 3D printed products, which include devices, living tissues, and prosthetics. So using the bioprinting technology and employing this edible bioink, the human structure can be built layer by layer to develop a human tissue. Different researchers, they are employing this for creating skin graft, knee cartilage, and small heart valves. So ongoing work is to create organs such as kidney, pancreas, or heart from human body, having enormous impact, thereby reducing the wait for donor or transplants, and controlling or curing the chronic ailments such as diabetes. So you don't have to wait for the patient or any donor. And if these 3D printed are approved, then you can use this directly in the humans. And the printing of cells or tissues from different body parts is almost at the nascent stage, because there is a lengthy ethical and regulatory approval process which needs to be followed for these to be approved and implanted. So, however, the ability to perfectly match and avoid donor weight would save countless lives. It is expected that this sector would hit the market in next decade, and then there would be a huge impact. The external wearable prosthetic device market, which we are also working, continue to lead the 3D printing healthcare market due to increased number of amputees, patients with auditory loss, dental problems, and increasing availability of advanced biocompatible material. Further, the production of personalized 3D printed wearable device will cater to the customized need of the patients by providing better fitting and comfort, thus improving market growth. extensively being deployed in the field of dentistry to provide precise, less invasive and localized treatment as per patient requirement. So bioprinting for tissue organs, you see these are the medical applications of 3D printing. So what are the medical applications? If you see, it is used for bioprinting of tissues and organs, for giving a unique dosage for pharmaceutical, personalized drug delivery, complex drug release profile, customized building of implant and prosthesis as per the need of the user, and anatomical models for surgical preparations before actual surgery can be performed by the surgeon. What are the future applications of 3D printing? It is used for printing organs and living tissues for organisms, which can be printed. It can be used for prototyping and build 3D models by different researchers and business industries. It can be used for manufacturing machines and robots and other devices. And it also can be used for food in printing this thing, because as you know, our population is growing and the food requirement will be enormous. So there also this can be helpful. And what are the challenges for this technology, 3D printing technology, to be adopted? The first is that the cell tissue bioprinting material is well suited with physiologically appropriate material. So you understand biocompatibility and all those things. And increasing the firmness and speed of these mechanisms and their commercial usage, improving biomaterial composition and cell source, developing vascular and nerve models, and understanding maturation model for every material is required. Then we have to understand the future role of robotics and nanomedicine in development of 3D printing technology. Also, we need to take care of biocompatibility and mechanical properties for cell support, which is required to assist the formation of soft tissue organs to be transferred into the human body. And the final question is about the possibilities of biofabrication. We will be having the required this thing to develop number of the products which we require. So like commercialization and other aspects. So the studies are going on to resolve viable economic way to commercialize organ printing technology, so that to methodically employ scalable automated robotic technology and build an assimilated organ fabrication line. The bioproduction of human organ requires improvement in assimilated automated robotic device. The other tasks that need to be overcome include advancement of different biomaterials and refining printed technologies to advance and get better results. So now you see this slide I have sharing with you. You see the 3D printed medical devices. It's being used in wound dressing. It is being used in implant processes. It is being used in surgical models. So in wound dressing, it is used for antibacterial dressing. It's used for vascular grafts dressing. In implant and processes, it's used for cast, stand, limbs, craniofacial implants. Then for surgical models, it is used as organs, vasculature, tumor models, disease models. And the material which is used, because some of you asked this question, so material they are using is silicon, titanium, hydroxide, nylon, PCL, PEG. And what are the advantages? You just see this. These are advantages are high resolution, good stability. It is more effective treatment. It can give multi-purpose material can be used. Good fidelity for patient anatomy, design of precise shape as per requirement, aesthetic and functional outcome, it looks good when you put them, increase surgeon skills and reduce risk of intraoperative complication, reduce time and cost for surgical procedure. And bio-inspired, bio-based 3D printing, you see bioprinting, cartilage, organ on chips. So here you're using materials such as nanocellulose, alginate, PCL, silicon, PDMS, all these material, and 4D printing is also coming up. So stimuli responsive hydrogel are there, which respond based on the stimuli, and actuators for robots that will definitely take it to somewhere a different scale. So it will be having more better resolution, it will be having good stability, it will be having low cost and possibility of manufacturing programmable devices with functionality and reduce risk of transplant rejection, stimuli responsive material, diagnostic tool, high proliferation rate and cell viability of 3D constructs. So all these are also there. And the 3D printing market, healthcare market, global market is projected to grow. Why? Because there is a lot of initiative by the government of different countries in this healthcare sector. And growing technological advancement in 3D printing is also there. As you know now, due to COVID, there is a lot of awareness on healthcare. So focus by many governments on this type of technology, and easy availability of material is there. Easy development of medical devices, less of the routine procedures and all those other aspects. Widening use of 3D printing method in healthcare industry. Then 3D printing is playing a vital role in dental manufacturing industry. It is cost-effective and favored option by medical device companies, comprising of different type of medical devices such as hearing aids, prosthetic, custom-made knee and hip implants. And 3D printing is projected to show major growth throughout the forecast period to several technological improvements in the medical field. What are the other influences such as R&D investment, rapidly expanding customer base who want to use these products, increasing the scope of biomedical area, application has led to more market growth, and some factors which may obstruct this growth of the market in future are adverse reimbursement policies. Maybe this device which you are using may not be acceptable or this thing. So all those norms have to be taken into consideration. So if somebody is getting a 3D printed kidney or 3D printed other device, this thing during a surgical procedure, then this should be accepted, and the patient should reimburse for those by the medical companies and insurance and all those things. Then high price of, so that has to be reduced. It has to be made more economical, so that, as I showed you in one of the YouTube videos, they were saying that it should go to every home. So it can be like your toaster oven or a microwave, it is there in every home. So same way 3D printers are there and people can use and print it. So for that it's a little far away, but still the signs are there for this. And biocompatibility issues of 3D printed medical devices and limited technical expertise available to deal with these type of devices. So there is one report by Allied Market Research, and they show that this market has grown at around 26.2% between the 2015 to 2020. And the 3D printed bioprinting market, it will show major progress in Asia Pacific and LAMEA zones owing to improved number of startup firms and awareness. And the external wearable device use market would increase to about 2.3 billion by 2020. And the hospital and medical centers are major end users of the market, constitute 3/4 share of total 3D printed healthcare market. So more of the hospitals and medical centers, they are using these type of devices which are approved. And the global market for 3D printing product is driven by several technological breakthroughs, such as use of multiple material, full color 3D printers powered by natural or renewable energy sources, portability and ease of use, huge investment by public and private organizations in the technology to drive the market, availability of customized, biocompatible, and personalized medical device, which is giving a good impetus to this market growth worldwide. With increasing population of elderly people and patients who are showing signs of osteoarthritis symptoms, also it is coming in the age of 40 years and so early age symptoms. For there also enhancement in the amputee population who are the war veterans or disabled due to some reason, and patient hearing loss or any type of dental problems, they would also further drive this market. Adoption of the technology, the duration of the surgery, exposure to anesthesia, risk from surgery, and by helping in pre-surgery planning, this will improve the practice of the surgeon before operating procedures. Therefore, they promote faster healing. Now, if you know about telemedicine, also before this robotic surgery or telemedicine, before the surgery is performed by the surgeon or this thing, they have to test and make it ready and compatible as per the surgery they are doing on the patient. The same way, this 3D printing technology to be adopted, the surgeon will also try to enhance his skills, try to improve his planning before he can go and do the actual surgical procedure. So 3D printed organs, they have provided alternative methods for animal testing. It will reduce the period for clinical trials, associated costs, and inherent risk associated with testing of new drugs leading to market growth. However, there are higher costs associated with this advanced 3D printers. There is a lack of structured regulatory works and reimbursement policies, along with copyright and patent issues of 3D printed technology, which can impede the market growth for these products. So these are some of my references for where I have taken this talk. And as they say that miracles come in moments, so we should be ready and willing for this type of miracle. And thank you so much for your patient listening and giving me an opportunity to share my views on 3D printing with you. Thank you. Namaste. Oh, no worries. I will share with you the audio. I will share with you the video so that all of you can go through it. I can play this thing again. अरे यार, what is this? So I'm done with my talk. I've done with my talk. So if anybody have any query, can ask me any questions, and I will share you with you the videos. I think they have no questions. So you can. Thank you so much.
Sir, I think
Thank you so much, sir.
audience.
Now we're going to have the last speaker of today's session, Dr. Pranjal Chandran. Dr. Pranjal is currently employed as an associate professor at the School of Biochemical Engineering, Indian Institute of Technology, BHU, Varanasi, India. He earned his PhD from Busan National University, South Korea, and did postdoctoral training at the Technion Israel Institute of Technology, Israel. Dr. Chandra has over 7 years of professional experience after his doctoral research. His research focus is highly interdisciplinary, spanning a wide range in biotechnology, nanobiosensor, biochemical, biodiagnostic, material engineering for diverse application extra. He has published 8 books on various aspects. He has 2 international patents, South Korea, and has authored over 90 journals in top-tier journals. Chandra's work has been greatly featured in over 450 news agencies outlets globally: India, USA, London, Canada, Dublin, China, Malaysia, Singapore, Taiwan, etc. Has also received appreciation by the Honorable HRD Minister, Government of India. He was the receiver of about 50 international journals and expert project receiver of various national, international funding agencies. He has delivered several invited lectures in national and international conferences and presented the keynote lecture in Rusa. I welcome Dr. Pranjal Chandra to the platform to present his speech on the topic Nano-Engineered 3D Dendrites and their Composite of Biomedical Applications.
Hello. Hello.
Yes, we can hear you, sir. Please share your PPT, sir.
Yeah,
Share your
Professor
screen.
Patia.
Yes, sir.
Oh,
Please share your screen. Yeah, video is also, we can't see. Video you want to put, sir? Dr. Chanda, you may start your presentations, please.
hello.
We can hear you, but screen is
No,
not
no.
seeing.
Actually it is keep on rotating. I'm trying to. There is
Okay.
some glitch, I think, in the connection.
Okay.
Hello.
Yes, sir, we can hear you.
Yeah, actually the problem is it is saying there is some problem in the sharing. I'm trying that.
Then you can do one thing, sir. You can send it to us, Dr. Dinesh Bhatia, or to me, so we can share it if it is not.
You can mail to either one of us if you want. There is one suggestion also from some participant that you can disconnect and connect again. You can try that, sir.
Hello.
Yes, sir, we can hear you. Please share your screen.
From my side, it is showing that screen has been shared.
No, you have to open the PPT.
No, I have opened the PPT already.
Now it has come.
All right.
Yes, you can please go ahead.
Okay. Thank you. And sorry for the delay. So I hope you can listen and see me very clearly, right?
Yes, sir.
Okay. Fine. Yeah. So hello everybody, and I would like to thank Professor Bhatia and the Royal Global team to invite me to give a presentation on the very upcoming area where we have also started, and last about 12 13 years we have been working in the area of sensing, but this is a very good opportunity for me to discuss the 3D, the 3D kind of materials and the composites what we have prepared so far, and how it is going to influence the whole process of the sensing applications. So that I'm going to talk today. So the presentation of what I'm going to talk is the nano engineered 3D dendrites and their composites for biomedical application. So my presentation contents will be, so what we are studying at the Indian Institute of Technology, Varanasi, and the nanobiosensor is a new wave of diagnostics. That's very, very important. And after that, I have included the additive manufacturing, 3D printed sensors and accessories, what very recently people are doing. So there are very recent papers on in 2019 and 20 where they have deliberately created very important and very interesting platforms that has been very uniquely utilized to develop the final sensing prototypes, and it is in fact very powerful compared to the normal electrodes or normal sensors. And then I will be talking about the 3D nano engineered surface and the materials for the sensing applications. So I'll, with this slide, I would like to share that what is the laboratory where we are working, what we are doing basically, what are the various fields we are focusing. And my laboratory name is the Laboratory of Biophysio Sensors and Nano Bioengineering. So these are the 5 major area what we are exploring in the laboratory. One is the material engineering and characterization, a development of commercially viable nano biosensing prototypes, medical diagnostics, and recently we have also developed the 3D nano engineering for sensing applications. We have recently created some modules and that we are testing at this moment. And next is what electrochemical biosensors, and the paper microfluidics and biosensor is also one of the very promising area what we have studied over the years. So basically, before starting with the materials or the interfacing things, I would like to mention that what we study. I mean, why we are studying these things. We are studying these things because we are interested to develop the sensing module. That is the final aim of our all research. So I mean, what we are sensing when we talk about the sensing word, we say that we are going to detect, and what we are going to detect, it's a various kind of the molecules. It could be a COVID-19 antigen also. I have deliberately put the blue color here, so it's a spike protein. And in addition to this kind of the proteins or the whole cell, you can go for the detection of the toxins also, like in case of the cholera or Shiga toxin or various other toxins. And you can go for the detection of the DNA, RNA, and protein level in case of the any bacterial infection. So collectively, all these molecules, they are called as a biomarker, And when we go for the detection of the biomarker in medical science, we say that we are going to diagnose a disease. So this is the whole layout basically of the basic idea behind development of any sensing system, right? So the on the right side of the slide it is mentioned that these are the very common techniques and highly powerful which people are utilizing to develop various diagnostic methods. But the problem in this case is basically they are very laborious and they require a very large sample volumes. If you talk about HPLC or some other ELISA based techniques, the initial sampling is, it requires a lot of volume. So the problem where we can work on is the development of a new methods, right, utilizing the novel engineering principles of nano engineering or bioengineering, and then overall that can be curtailed. So collectively the major challenges in the case of medical diagnosis and healthcare is what? The quick detection, on-site detection, and ultra sensitive detection. And the answer for these issues are what? The biosensors or a nano biosensor, which comprise various type of materials, including the three-dimensional materials what I am focusing today majorly. So the nano biosensor is nothing, it's a bioanalytical device that utilizes a very specific biochemical reaction which is mediated by various kind of receptor what is mentioned here on the slide. It is antibody or a peptide, aptamer, enzyme, or a DNA, RNA. So this basically bind with the receptor molecule, and when it binds with the receptor molecule, it gives rise to a biological event, and then this biological event has been translated into a readable signal using a transducer system. So basically, after the interaction of the biomolecules with the receptor, we are getting the signal output. So the major two components is what is the bioreceptor and a transducer, which is very much important in development of any biosensors. So these are it is also called as a new wave in diagnostics because you can see over the years the publication is keep on increasing and it is a very high world business market over the years. So the basic thing in this case is what? Whenever you are incorporating such kind of the material in the system, so it improves the sensitivity of the system and we can go for an ultra sensitive analysis. That is the advantage of such kind of the biosensors, right? So this is some of the recent reports where it says the overall what is the business market of the biosensor incorporating various materials. So the analytical lab, what we can see in the near future is something like this. So that is called as a lab on a chip technology. So you can integrate all the setups, whatever you are doing separately on a single chip, and then you can work and you can detect various molecules and you can diagnose a disease eventually. By this slide you can very clearly understand how 3D printing is going to help this system, right? This is a 3D printed material or on a chip where this has been utilized for the microfluidic system. So I will be talking with few examples that how the printing technology is going to help the development of the sensor, the application of the sensor, and how the 3D printed material or 3D engineered materials is going to increase the sensitivity of the system. So that is the overall idea in this case. So I have taken a very recent publication for the electrochemical sensor, all the thought of the 3D printer towards sensors basically. So this is the basic structure. Everybody know that this is the printing system, and then these are the all possibilities where we can utilize this printed technology right from the development of the cell, in addition to the development of the material onto the surface, the tubings, the other assemblies, and so on, even the electrodes. So this type of the printing technology is very powerful and it can be utilized for all the aspect of sensors, not only the construction of the fabric system, or not only the construction of the analytical system, but also to the material coating also. That is also very much important. So the 3D printed biosensor have various importance. It contributes to the development of 3D printed to fabricate the tunable electrochemical sensor. It means it can be scaled down or scale up. That is very much important. And the different 3D printing modules can be performed nowadays in order to improve the efficiency of the system. And the most important thing, the various other material can be printed onto the surface. So I'll give you the example of in the later slide of a graphene with a PLA, polylactic acid. You can coat it you can prepare the composite of this one and you can transfer it onto the surface of the electrode, and then eventually you can go for the analysis of any kind of the molecule. So this is the advantage. You can tune it the way you want. So eventually as I said, not only the material but the whole electrochemical device can be fabricated nowadays for the by incorporating the 3D printing system. So this is the example, a very new example where a 3D printed electrode has been used using the carbon black. So this is the pictorial representation of the system, how they are printed and what are the, I mean, the inside of that. And this is the final VP electrode is a vertical printed electrode, and HRPC is a horizontal printed rough electrode. And when it has been smooth, you can see HPSS. I mean, what I'm trying to explain by this slide is what the electrode material can also be can also be created by using a 3D printed system, right? So this is also one another example very recently published in nanoscale, which clearly demonstrate the application of the 3D printing in the development of nano sensors. This is the classical setup of the 3D printed. Everybody know that. As I said, the graphene can be incorporated with the PLA, and then you can get a final product of a 15 size. You can transfer this setup onto the electrode surface, and it will be it will be a surface where the enzyme can be immobilized. So after the immobilization of the enzyme, this can be subjected for the detection of other molecules using the electrochemical setup. So by this whole process, it is very much evident that when you are incorporating this very stable system of graphene PLA, that can be work as a transduction system in a very powerful manner. So this is the example of one naphthol oxidation using enzyme mediated. This is the whole process, and this enzyme has been incorporated onto the 3D printed graphene PLA setup, right? So this is another example. Sorry, yeah. So this is another example of additive manufacturing where the macro electrode has been designed, and this is another example where a macro porous electrode has been designed. So the point here is what? Basically, any type of tunability is possible when you are working with the 3D printing with reference to sensing application. So the size, the dimension, you can see more or less. If you see the size of any system in a screen printed system, it is almost same, but you can design the way you want. You can tune the material. If you are interested in graphene, you can go for a graphene. If you are interested in end-doped graphene, you can go with that end-doped graphene also. If you are interested in any other material, carbon-based material or any other material, you can simply coat it onto the surface of the electrode by using a 3D printing system. So eventually, as I said, not only the electrode but the whole setup. This electrode, what I am showing in the blue setup, this is basically a commercially available electrode by Palmson's company from Netherlands. But this setup has been created where the whole 3D printed cell has been developed in order to detect the molecule using the electrochemical setup. So conclusively, by this all discussion, I am trying to convey what the electrode material, the fittings, and other cell can also be created for the electrochemical sensing application. So until this point, I have talked about the 3D classical, 3D printing system, where how it is going to help for the biosensing application. So after this slide, I'm going to talk about the nanomaterial, what we have developed in the laboratory, and how it is going to, assess the whole process of the biomedical analysis. So the basic idea in any sensing system is what, whenever we are incorporating a nanomaterial, we are talking about a sensor performance, right? So the sensor performance says, it means, if you see the slide in this one, there is a case of hypoglycemia and there is a case of hyperglycemia. So in case of hypoglycemia, we are talking, whenever we say hypoglycemia, we say the concentration of glucose is less, right? Or whenever we say hyperglycemia, the concentration of glucose is high. So what we are talking, we are talking basically the level of the compound, right? So whenever we are making any sensor, we are targeting for the level. And if the sensor is able to detect a very wide range, if you can see this black part here, if the sensor is able to detect from 80 to 140, it is not very much appreciable. So we need to have a sensor which can go for a low glucose and which can go for a very high glucose. It means from say for example 30 to 400 or 500 glucose concentration, if it is able to detect, then we are very much interested in that type of sensor. So based on this concept, there is a very straight line plot, which is the dynamic range, which is very important. The dynamic range should be as wide as possible. So that is a take home message from this slide. It means the incorporation of 3D materials can definitely going to improvise the dynamic range, and eventually it is more commercially viable, right? So this is the general information about the nanomaterials and the biosensors. It improves the detection range, it improves it stabilizes the system, it is very robust, and so on. So eventually the performance and everything is related with the type of the nanomaterial, especially the 3D nanomaterials, what is present in the matrix. So this is the general feature about the nanomaterials. Like it has a tunable optical, electrical, mechanical, magnetic property, and optoelectronic properties. So the classification overall given by Frank in a book published from Willy, they say that overall classification of nanomaterial is like this. But if you browse some other reliable source or any textbook, they have a different classification also. But I will not talk of other classification methods. I mean, all other materials. I will be talking about dendrites, because this is basically a tunable three-dimensional nanostructure which will be present onto the surface of the electrodes. Right. So whenever we make a sensor system, we are interested that what we are going to detect, and based on the what we detect, we develop the scheme and we do the fabrication. And whenever we do the fabrication, we need to characterize it. It means whatever we are talking in terms of the idea, whether it has been experimentally verified or not. So after this process, we are going to optimize the system, and we will go for the analytical performance, the analysis in the real samples, if for example in a blood or in a serum or in an environmental sample anywhere, and we go for the interference analysis, whether the sensor is selective or not. And finally, we will check the stability of the system. So this is the overall idea when we start studying about the nanosensor system. So these are the sensing modules what we have developed in the laboratory utilizing various other materials. I'll not go in the detail of this part. So now we'll come on the nano bioengineered 3D dendrites, what we have developed in the laboratory. So these are basically based on the electrochemical readout system, where this is a 3 electrode system basically. If you talk about the electrochemical cell, and as I have shown earlier also, this part can be very much designed using a 3D printer system, this part. But conventionally it is a glass based setup, and these are the different electrodes. The outer design, which is made up of Teflon, can also be designed using a PLA, and eventually this is being utilized for the development of the sensors, right? So this is the basic idea of the electrochemical sensor based on the oxidation reduction reaction. There should be a redox reaction, otherwise we will not get a signal in terms of the voltammetry. And then when we apply the specific potential, we get an oxidation or reduction signal. So this is the data which is going to come with this type of data, rather it will be coming in each and every slide wherever there is a analysis of the data, right? So this is the overall, I mean, the idea of the electrochemical sensing. So now the typical examples where we have utilized the three-dimensional materials. I have taken 4 examples. In the first one, we have developed a 3-dimensional nanostructures onto the surface of the indium tin oxide electrode or chip, dendritic chip, and it has been utilized to detect the hydrogen peroxide in the blood sample directly. Second is we have developed a nanohybrid system. This nanohybrid system was serving as a surface for the development of the 3-dimensional nanostructure again. And this is another unique system where we have utilized 2 different type of materials in order to develop 3-dimensional nanodendrites. And this one is more complex, where there are multi type of material, right from gold nanoparticle to 3D nanostructures, graphene oxide and other things has been utilized to develop the protein based sensing system. So if you talk about the metallic nanodendrite structures, this is a naturally present system This is a neuronal cell. I mean, I'm trying to convey that what is a dendritic nanostructure. I mean, what is the idea? What is the thing behind it? So these are the silver ferns, and if you just put a hammer on an eye, you will get this kind of a pattern. So this pattern is possible to create onto the chip in a 3-dimensional way. So I'll show the exact images. Maybe that will be more clear. And it also depends on the type of the process what you are adopting. So if I talk generally about the nanodendritic system, it is a very powerful structure which has a lot of electroactive sites, edges and corners, and it facilitates the process of electrochemical reaction or a chemical reaction. And most important thing is what? It is a diverse structure, and it doesn't allow the poisoning of the surface also. That is also very, very much important when you select any 3D structures. So this is the mechanism of the electrochemical dendrite formation, where you have a precursor molecule, and after this precursor molecule there is a nucleation of the dendrite formation, and with time it keep on growing and it form eventually the 3D structure, something like this. So this is the cartoon of that, and in the whole process of the formation, the diffusion limited aggregation is actually happening in the whole process. So this is the pictorial representation, and when we go in more detail, I'll let you know that how it looks like onto the surface. So this is the example number 1, where we have developed, as I said, the nanodendrite chip for the hydrogen peroxide detection. So in this case, we have attempted to show the waste to value based concept, where the chip what people usually throw after the process of the scanning electron microscopy, that chip has been utilized to develop the whole sensor system. So as I said before also, you have to do the nano tuning here. So this is the surface. When you create the when you are creating a three-dimensional structure, we create for various time intervals, right? You can see from 500 to 1500 second, when we are increasing the time, the patterning is changing, and eventually after I mean, this is the final uh, optimized data. At 1500 seconds, this kind of the pattern structure it is forming, right? So after this process, what is happening, we have to characterize the surface. You can see very clearly in the black and red curve that electron transfer or the data output here, it is less compared to the formation of the 3D structure. The signal output in terms of the current is very much high. It means the surface is conducting, and when we check the complementary data with reference to the resistance, the red has a less resistance. It is something about 28 kilo ohms, but and in this case the current is relatively higher. So these two data is complementing each other. It shows that the 3D structure what has been formed onto the surface is working very well, and this data is related with the stability that I will not go in the detail. So this is the final imaging system. So everything what I said, it is happening on the ITO glass. It's indium tin oxide, and this is the normal imaging of the SEM. And this is basically I'm more interested to talk here. So this is the final image, what it looks like. And if you take the X, Y, and Z, it is growing on all the directions. So that is why we are calling it as a three-dimensional structure, which is forming on the electrode surface, and it is extremely controlled manner. Right. So this is very much important, and it is a homogeneous distribution on the active side. Right. So again, as I said, we have done a lot of electrochemistry here, and we have controlled the diffusion coefficients and other things in order to confirm at which surface maximum transfer of electron is happening. So we found that at ITO and after the sputtering process, the maximum the diffusion coefficient is the highest. So after the development of this 3D chip, what we have done, we have employed this for the detection of hydrogen peroxide because it has a lot of clinical and biomedical applications. So after this process, this is the whole schematic representation of this particular work. Is the electrode followed by the deposition of the nanostructure, then the sputtering of the nanostructure, and then electrochemical reduction of the whole process. And this is the signal output, right? So this is the response of the hydrogen peroxide of various controls, and this is the response of the hydrogen peroxide with increasing the scan rate. It is very much stable, and this is the initial response of the hydrogen peroxide with the high concentration. This data is very much important. If I say, you can see in 1 second, or more precisely in less than a second, it is giving a signal response. That is only because of the incorporation of such three-dimensional nanostructures in the matrix. So this is the beauty of these materials in the sensing matrix. Less than a second also you can get a signal output. So after this process, we have done the calibration response. It means with the dose, we are increasing the dose, the signals keep on increasing, and it's as wide as possible you can see. And eventually the detection limit in this case was 9.8 into 10 power 13 moles, which is the lowest reported until last year, because we have got this paper published last year, right? So this is the interference data. I will not go in the detail. And this is the real sample analysis, what we have done in the blood. In the standard condition, in the blood condition, it is behaving more or less very same. And not only in the blood, if we are going to detect the hydrogen peroxide in the milk also, that is also possible, because FDA approved the maximum concentration of hydrogen peroxide in the milk is 10 to the power 6, and our sensor is able to detect from 10 to the minus 5 to 10 to the minus 12. So this is very much important. So this is the comparison. As I said, it has the lowest detection limit reported until 2019. So this we got some media highlight also, where we have developed a waste to value chip kind of thing for the detection of hydrogen peroxide in various systems. Right. So this is another three-dimensional bimetallic system, because earlier was a monometallic system where we have utilized the gold system. This is a bimetallic 3D nanodendrite where we have utilized to develop it onto the surface. I have discussed this part already. I'll not go in the detail of that how we have created it. This part is more important actually. You can see very clearly this is the bare electrode at this one, the black one. But when we have engineered the gold and copper together, the signal is maximum in this case. That's why I have circled this part also. And complementary to this one, the resistance of the surface having the both the gold and copper dendrite, it's least. It means the highest electron transfer. So these are the pattern structure as I've shown earlier also, but this is for gold, copper and gold both. And this is also the optimization time I have what I have shown earlier also, from 10 seconds to 600 seconds. Until 600 seconds, the maximum three-dimensional and structure has been formed onto the surface of the chip. So this slide shows basically the presence of both copper and gold in the matrix. So this is the dark field time image where you can see this is the normal situation, and this is the copper base, this is the gold, and when we have merged it together, you can see the gold and copper, they are present together. So after this process, we have tested the response in the system containing the target molecule, and the maximum signal you can see the blue curve, it is based because of the bimetallic gold and copper 3D structure, and this is the stability data of this one. And after this process, what we have done, we have checked the response of what acetaminophen in this case. The acetaminophen is the basic target molecule. When we were keep on increasing the concentration of the acetaminophen, the signal is keep on increasing from between 100 to 1000 nanomoles, and this is a straight calibration plot which shows the limit of detection of 8 nanomoles, very less actually. So this is the interference data where you can see the closely related compound which is present, which coexist in the with the acetaminophen. They have no signal, and in the standard condition as well as the detection of the acetaminophen in the urine sample is also very much. I mean, it is quite well. You can see the data, right? So the third example is the nanohybrid development. We have developed a nanohybrid in the very first case where the gold nanoparticles and multi-walled carbon nanotubes had been utilized, and then this was used as a surface where a dendrite has been grown. Right, you can see first what we have done. We have prepared the gold nanoparticle and the nanotube. You can see all this data here: SAD imaging, PDX, and mapping. Also, you can see the presence of carbon and gold in the whole system. Right. So this part and this part is basically same. The patterning is only different. This is the physical characterization. And after this process, as I said, we have used this as a matrix. You can see the gold nanoparticles. These are the fibers. Over this fiber, you can see very clear-cut tree-shaped structure has been formed here, which is again a dendritic structure. We have zoomed in this part. You can see this here, the nanorods as well as the particle is very much evident, and we have zoomed in this part. This is a three-dimensional structure again, which is a tree-shaped structure. What we are discussing since all the examples, and this is the again the mapping part, because this is made up of gold, actually gold three-dimensional structures, and this is made up of carbon, and this is the gold nanoparticles. So you can see the presence of all three components in the sensing matrix. So this clearly shows basically the presence of all three materials and the formation of a very powerful electrocatalytic catalytic material, which is a dendrite in this case. So again, in this case, what happened? We have again checked the performance of the chip where the maximum signal was obtained with the nanohybrid comprising the 3D nanodendrites. And again, in this case, the resistance is least having the nanohybrid containing the 3D nanostructure, which is a dendrite. So we have checked the performance. You can see the glassy carbon electrode is here, which is a bare electrode. There is no modification. After the modification containing all the materials, what I said earlier also, the signal is completely improvised. And there is a shift also towards the negative potential. It shows that there is a electrocatalysis is happening. We have increased the concentration of acetaminophen from 10 to 50, and there is a straight line which is forming, which is showing a very good correlation between the data. So this is the final, the calibration where the concentration has been increased from 100 to 7,500, and there is a very clear-cut increase in the signal. You can see from this calibration plot, and the response time is about 10 seconds. I mean, we have done multiple testing. We can say about 8 to 11, 12 seconds. The response time is there. So this response time is basically attributed because of the presence of these nanostructures in the matrix. Otherwise, if you remove the nanostructure matrix, there will be no, such robustness in the system, right? So this is basically the interference of the closely related molecules which coexist in the system, and this is the mixed sample analysis. It means we have added all these molecules together with the target molecule, and you can see it is almost similar to the molecule when we are tested it separately. This is with the standard condition data, and this is the real sample analysis where we have tested the urine samples. So this is the chip to chip variation, and this is the long term stability. It means when we incorporate such materials in the chip, there is a very minor variation, and whenever we incorporate this material in the chip, the shelf life is quite high. It is about 2 months. That is very much important for commercial perspective, right? So this is the comparison of the data. I will not go in the detail. So this is the last example, which is a very typical, and we took about like more than a year to develop this kind of the patterning system, where we have developed the electrochemical immunosensor for the detection of CEA. It's a cancer biomarker, and we have incorporated a very optimized system. This is actually the real image what we have obtained. This is a very unique three-dimensional structure, right? After iterative process of optimization, I will not discuss the whole process of optimization, but we have done a lot of, I mean, about several months we took to obtain these images. So this image, I mean, this structure was incorporated in the whole matrix in order to develop the final sensing system. So this is the, we are in, we like this work a lot. Okay, so this is the general information of the cancer biomarker CEA. Will not talk this. So this is the whole idea. This is the whole schematic representation of the sensor development. We have taken a chitosan, we have taken a RGO, we have taken a nanoparticle and a nanodendrite, all the things. We have layered it onto the surface layer by layer, and then we have anchored the antibody. So in this example only, I'm talking about antibodies. Otherwise, other example what I have talked, it was based on the direct electron transfer DET, but in this case we have used the antibody based sensor, right? So we have anchored the antibody in this case, and then there was a immunocomplexation, and then we got the signal output. How it is going to happen, I'm showing in the next slide. So this is some other kind of the recent reports in 2019, which we have developed the bare gold dendrite electrode. So the problem in this case is what happened whenever you use a metallic surface for the analysis of any protein, so it has a tendency to adsorb onto the surface. So that is the reason we incorporated a chitosan in the system, right? Because that was not allowing that kind of the fouling in our experience. So that was the plot basically of our investigation based on this work. So we have developed the sensor system by forming the nanoparticles onto the surface. You can see this is the formation of the nanoparticle gold, where the current is keep on increasing. You can see on the y-axis, it means the conductivity is increasing. And similar data, this is also showing the similar kind of the data. This is the method what we have followed for the development of the chitosan. We have used the shrimp cell in this case, and this is the characterization of the chitosan from the prawn. You can see this is the commercially available chitosan. This is our lab prepared, the red curve in both the case. And then we have developed the step-by-step layering. As I said, we have done step-by-step layering, and then we have characterized the surface. I mean, these curves basically shows that how the chip is behaving when you are making the, when you are layering various compound onto the surface, right? So this is also done for the characterization of the electrode, which says that the surface is very much stable. And this is a physical characterization. You can see these structures, they are homogeneously distributed onto the chip, and which participate in the generation of ultra fast signals. Because what we have done, we have removed this system from the matrix here, and we have tested the whole sensor without this material. So when we have removed this material, the signal was dropped drastically. I mean, we are not saying that signal was not coming. The signal was coming, but by incorporating these materials, these 3D materials in the matrix of the sensor, the signal was improvised several folds. So that was the beauty of this particular work. And again, we have tried this part. You can see, so this is the normal imaging system, and we have done the mapping of the this one, the electrode surface. This is the gold, this is the carbon, nitrogen, oxygen, and when you merge it all, so it is very much evident that all materials are present on the surface. So this is the final calibration. We have increased the concentration from -8 to -30 in order, and you can see the signal is keep on increasing like that. So this is the calibration, and this is the real sample analysis. This time we have taken the serum sample because CEA is present in the serum. So, and we can see the recovery of the CA in the matrix is quite well, about 93 to 99%. We can recover the CA if we are spiking it in the standard serum samples. So these are the interference. We have tested again the other cancer biomarkers and other proteins and other small molecules all together to show that the sensor which has been developed, it is highly robust and highly powerful. So this is the chip-to-chip variation and the stability data. And this is also one of another unique work what we have done recently. This is the last example what I am discussing in my presentation. This was actually done by, it is kind of a, how to say, it is a, we were aiming for three-dimensional, very defined nanostructure, what I have shown so far. But in this case, we have mentioned here, if you see the slide, we have mentioned dendrites, not dendrites, because it was not that particular, I mean, morphology. It was something different, but that different was also homogeneously distributed. So that is why it is a dendroid. It is dendrite-like structure. So this we have utilized to develop a sensor for the detection of alkaline phosphatase ALP, and we think that why it is happened because the seeding, because of the gold nanoparticle in the stage number 1, this part, it is making a different kind of, I mean, this is our assumption, we don't know whether it happened or not, we are thinking only this made a different kind of the seeding reaction here. So that is why maybe the dendrite which is formed, it is not a classical dendrite, but it is also a branch structure. So what I'm trying to explain that this type of nanostructure is very much possible for the implication in the development of sensors, right? So I'll not talk this part detail. We have published this paper just recently in Biosensors and Bioelectros, which is one of the top one in our area. And the prospect is what the receptor can be loaded with other biomolecules. I mean, we can change this antibody with other antibody. The multiplexing is possible, and it takes nearly 15 minutes for the detection. It's a label-free technology because we are using a electrochemical impedance spectroscopy. And the last, which is most important, what this system can be integrated with a smartphone, and we can get the personalized diagnosis of ALP. Right. So the overall conclusion and the vision is what the 3D assisted system can be utilized for the development of various sensors in a personalized diagnosis, and we are always aiming for a new material that can be engineered for diverse sensing application. And the multiplexing is very much possible when you are talking various materials. And eventually what we are aiming for commercially viable and viable sensors and the product development. And again, and if somebody is working in the area of biosensor, we need to have information of these areas such as instrumentation, biochemistry, basic biology, clinical science, chemistry, material science, physics, and so on, market requirement. Because this is very important, because if somebody is not going to be utilized by the general public, there is no point of making that kind of device. So what information we are going to deliver as an analytical chemist? We will be developing a sensor based on the biomarker information from the clinician or any other people who are working in this area, and we will be delivering the analytical information. We will tell the values that this is the level of this compound, either a glucose or a compound in the soil, or whether a cancer biomarker or anything. So I'd like to acknowledge my whole team, my PhD students present and graduated, and the funding agency who has significantly helped me to develop the whole lab and the facility. And thank you so much. So our tagline is that we can mimic the nature to develop better diagnostic device. I have deliberately talked about the dendrite in this section, so I have put this beautiful fern. And again, I would like to thank Dr. Bhatia for inviting me, and the Royal Global team. So they have given me this opportunity to discuss some of the work. So although the classical 3D printing, what is the overall mandate of the conference, has been, I mean, we are doing that, but these materials is definitely can be layered onto the designed electrode materials, and we are looking forward to have that kind of technology very soon in our laboratory. Thank you so much. Hello.
Well, I think Dr. Bhatia is offline right now. I sincerely thank you, Dr. Chandra. I'm Shashank from Royal Global University.
Yeah, thank you.
I think Professor Bhatia is having some connectivity issue. I don't see him online right now. So definitely it was a good session, although I couldn't much of it because I was at the back end. So let's hope to hear some more talks tomorrow. Hirok, this is the last session, right? For today. So thank you everybody for joining in, and we have shared the feedback link. So kindly fill it, and hope to we'll see you everybody tomorrow morning again at 10 a.m. Thank you everybody. Okay, Hero, can you see if Professor Bhatia has joined? Well,
he is not here.
Okay. Then thank you everybody. So we will meet tomorrow morning again. So I'll close this meeting for the day, and kindly fill the feedback form. Thank you. Bye, Dr. Chandra.
Thank you. Thank you.